Welcome everyone to this webinar hosted by Multimechanics. Today is the official MultiMech 19.0 release webinar, where we'll go over all of the new capabilities in this new version, as well as perform live demonstrations of a few of the new additions to the software. I'm your host, Aidan Cornwell, and I'm a solutions engineer at Multimechanics, where I assist our users to utilize our software to solve the most difficult engineering problems, as well as grow the applications of our FEA tool. With me today is Flavio Souza, who is the co-founder, president, and CTO of Multimechanics. And he will be a panelist that will answer any questions you may have at the end of the webinar. Speaking of questions, please locate the Q&A button on your Zoom application. This is where you can ask any questions you may have of the software. Please feel free to ask the questions at any time during the presentation. The last thing we want is for you to forget the question by the time the Q&A session rolls around. Okay, now that I've covered the introduction, let us begin the webinar. Here's the agenda for the presentation today. First, we'll give an overview of the MultiMech software and just how the core technology and just how this software came about. Then we'll go over the new features on the 19.0 release. We'll dive a little deeper into a few of the new features, 3 features to be exact, which are the material database, Bi-modulus material model, and the virtual DMA. And we're pretty excited about these 3 different capabilities because these have been requests for customers for quite some time, and we're very proud to be finally releasing and demonstrating them. At the end, we'll do a brief conclusion, and then we'll do a Q&A for any question you may have, and me and Fabio will do our best to answer any of those questions. So first, what is MultiMech? MultiMech came around because, as a few of you may know, failure prediction in engineered materials is extremely difficult. And when I say engineered materials, I'm not only talking about fiber reinforced polymers. I'm also talking about materials that are classically seen as homogeneous or isotropic. Even for alloys, which are seen as isotropic, at some length scale, you start to have inclusions, cracks, things that aren't necessarily homogeneous. So these materials can really be represented at the microscale as well, instead of being generalized as a homogeneous material. Basically, when you look at the failure of these materials, you have a lot of different microstructural failure mechanisms that slowly start to build as you increase the load, and a lot of these modes of failure start to coalesce, and then eventually you'll reach a catastrophic failure of the entire part. To characterize the failure as accurately as possible, you really do need to represent the microstructure. And this is why we consider this a true multi-scale problem, because if you have a part that is a meter wide and you have fibers that are microns in size, you're not going to be able to represent every single fiber in a meter part. Your mesh is not going to be that refined, and that simply is not feasible. So you really need to go in between these scales in a multi-scaling method. So that's where our true multi-scale technology comes in. What we do is we represent the global part and the microstructure at the same time for every single load step at every single integration point. Here's a benchmark to more accurately show what's going on with our simulations. Here we have a gear, and as it's being loaded, you'll see some blue, which represents a lower stiffness and the failed elements. If we zoom into 3 different integration points, we'll see we have 3 different microstructures. As the load begins to increase, you'll start to see different failure mechanisms originate in these microstructures in different ways. We see some have cracks going diagonally across the RVE, some going vertically and horizontally. And this is really showing that we're looking at 3 different microstructures that have 3 different load cases. And with different load cases, you have different forms of failure or different ways that it's going to fail, whether it's under shear, tension, compression, etc. As you imagine, with 50,000 microstructures, and each microstructure having, let's say, 2,000 to 3,000 elements, it's a lot of degrees of freedom. And this used to take a really long time. This methodology is the FE squared approach. And we're taking the same route. However, we've applied data compression algorithms to our software, and we're now able to do these calculations with a drastic reduction in memory and runtime. Originally, this model would have taken about a month and a half to run, which simply isn't feasible for the commercial sector. And we're able to run this now in 40 minutes. Same thing goes for memory. You're not going to have a lot of computers that have 1.5 terabytes of RAM. We're able to do it at 5 gigabytes, which we ran on most laptops. Another demonstration of a MultiMech multi-scale simulation. We're looking at a leaf spring here, and again, we're pointing to 3 different RVEs. To be completely clear, RVE stands for representative volume element, which is the smallest microstructure that represents the material as a whole. As we load this leaf spring, we'll see in real time how each RVE is loaded. RVE1 is under tension, RVE2 is under compression, and RVE3 is a ply that is angled away from the direction of the load. So we're going to see some in-plane shearing in this RVE. What you see here is we start to see some damage start to evolve within this microstructure, and around cycle 5 or 6, we see that this damage reaches a critical point, and we lose all stiffness in that ply. And you see how in the global part, we have all this different stiffness that is lost in the red areas. We got a lot of recognition for this data compression, speed increases on this methodology of finite element analysis at other different startup competitions, also composite trade shows. We have partnerships with other large CAE companies. We don't necessarily mean to replace these different types of analysis and simulation. What we want to do is we want to enhance it. That's why we made a few different plugins for ANSYS, Abacus, as well as NX Nastran. And we don't want to disrupt the engineering workflow that's currently in place in companies. We want to enhance it with a more accurate solution where you can represent a microstructure when you're simulating these composite materials. Most importantly, our customers love our software, even at different levels, at the executive level. They see it as a lot of potential to help increase the productivity of developing, say, materials or components. And even at the user level, they're seeing it as a very streamlined, easy workflow to run more accurate simulations. Now we'll go over the new features. First, the material database, and this is where we can now have a unified database that can store any of the materials that you made, any of the microstructures, anything really that's created through MultiMech, you can now save and organize through this database. You can create multiple databases. Let's say you want to have a database for all of your resins, or a single resin with different material models represent the resin. You can do that. You can organize it in a lot of different structures. We also have some new material models. One of which that we're going to go over today is the Bi-modulus model. And Bi-modulus means that you're going to have a different modulus when you're under tension and compression. We also included the nonlinear model too, so you can incorporate things like strain stiffening or strain softening behavior. We also have a few different continuum damage models that show a little bit more progressive failure as opposed to just generalized failure. So this is something that's really helpful for if you want to use a failure model, but you don't want a sudden drop in stiffness. You can have more of a gradual stiffness loss at a certain point. We now have a virtual DMA, and we'll go into details behind this, but a lot of times in composite materials, it's very hard to do the DMA analysis with a different load case of a composite. These materials are intrinsically orthotropic, so you're going to need to do a DMA in all the different directions. With the virtual DMA, you can just characterize the resin, which is viscoelastic, and then you can run the rest of the DMA analyses virtually. Finally, we have some performance improvements. Every single time we do a new release, there's always going to be performance improvements. We're constantly making this software more and more efficient. And we also have an integration with ANSYS Design Explorer, which we'll probably have a webinar about at some point in the future. Now we'll go into the material database. So like I was saying, you have a lot of different combinations of materials, material models, microstructures, meshes, etc. And when you do a lot of work to find a good microstructure that's really representative, or you create 5 microstructures that are really representative, it's really hard to organize all these because you have a lot of different project files, you have a lot of different material models. You don't want to save them in the materials within the GMM because then it would be harder to find. So we decided to create a database that can hold all these together. You can search through different tags where these different material models are. So here's a demonstration. You can open your material database through the material library. You can see how we have 2 new buttons on the right here, the open material database and save to material database. You can open it and we see we have our database here. It'll open to the most previously used database. So we have a few different RVEs that are already saved as database. You'll see that we have a name, type, tags, and units function to list here. So you can change the way these are listed. When we look and select the material, you can see they also have an image on the right. It will specify in the type that if it's a microscale RVE or if it's a MultiMech material. It'll specify that, and it'll specify if it's isotropic, orthotropic, or any of the different material models that we have. You also search the different microstructures through the tags. So let's say we want to look for all of our injection molding RVEs. We want to look for all of the unidirectional RVEs. We can search it that way and filter out all the different things. And we also have the image name because it's really hard to just look at this and know exactly what's going on. So we have the opportunity to document the mesh or the results. You can do a stress strain curve. You can do a lot of different things to make it easier for someone, if you're passing this database along to different people within your organization, to know what kind of material this is. We get a better understanding. What we can do here is we can now add new materials or microstructures through the new button. We can also edit different ones here. In this case, it's an RVE, so we can replace the RVE if we decide we want to have a RVE that's more representative of the microstructure. And we can also edit the description here. You can also delete anything you'd want out of this. To bring one of these materials or RVEs to your microstructure, you can simply select this and select add to model. And we can now see that was added successfully, and we can see this new RV represented here. And we can go the other way around. We can take a material that's in this GMM and bring it into the database by selecting save to material database. And we say we have a couple of RVEs listed in the material library. Let's just do continuous fiber. And we have the option to select units, damage type, runtime, etc., and add tags. So let's make a different name because that one is already existing. And the database noticed that there are multiple materials in the RVE as well. And it'll ask you, do you want to add the materials? So we say, sure. Now I'll give you the option to add different materials. So we have e-glass and resin here. So you add those, add any descriptions or units that you want, and now we have some materials. We can filter out the RVs and materials by selecting the RVs button right here. So this can be used to save a lot of different types of materials. Now what we can do is you can also import from other different databases through the import materials button up here. In this case, I have a second database right here. And we see all these different material models here representing a wide variety of fibers. You can also do the same where so I had the RVs checked. So here's all the new material models that you have. We can now export all these different models. So if you want to create a specific resin or a fibers database, you can do that as well by simply exporting different materials here. So that's a brief overview of the material database. It's really up to the user what to do with it. You have now this ability to save and organize all these different materials into different groups and different organizational techniques you want. And you can finally have a solidified place that can have all your different constituent materials, your RVEs. It basically creates a best practices approach for saving all these different microstructures. So this would be really helpful for passing along and keeping materials saved when you pass on to different engineers, or even if you're working with us, we can pass you databases that have their materials. We can help you out in that regard too. Next, we'll go over the Bi-modulus material model. So when I say Bi-modulus, here's a depiction of the properties on the left. For a linear material, we see that in tension we have a certain modulus. But under compression with the Bi-modulus material model, we can have a different compression modulus as shown here. We can also add a nonlinear factor. The nonlinear factor it allows for either strain stiffening or softening behavior of your material through a nonlinear factor that I'll show you shortly. This is important because a lot of materials out there actually do have different modulus under tension compression. One that we'll go over specifically today is carbon fiber. But there's no limit to different type of material you can apply this material model to. We have isotropic bi-modulus material models, we have orthotropic bi-modulus material models, and then, of course, the bi-modulus material model with a nonlinear factor. And this is really important for parts that are under tension and compression. A lot of times, a very common test for continuous carbon fiber reinforced polymers is a 3-point or 4-point bending test or a short beam shear test to look at the interfacial strength. And these components are going to be under bending a lot of times too. So you have parts that are under tension and compression. So you need a material model that you can apply to one part that behaves correctly in every single load case. Show you a demonstration of the RV that we're looking at today. When we go to the material library, you'll see I have 3 different fibers already created. Here is a material model that we've been used in the past, and we see here we're looking at a modulus that this is the modulus under tension. This is the tension you can get from single fiber testing. And we know that if we use this and we try to run a compression test, we'll be over predicting the stiffness of the composite. So what we do is we apply a bi-modulus material model, and very similar to the orthotropic linear, but now we're looking at a tension and compression criteria. So we can go in between these different ones and we see how we have a higher tension modulus than compression modulus. And finally, to add the nonlinear factor, you have the same material model shown here, except now you have this G variable. The G variable is the nonlinear factor. So in this case, when it's positive and under tension, it will be strain stiffening. So I applied this factor. And when we run some virtual tests here, just to see how it behaves under tension compression to validate the material model, we'll see an effect like this. The blue line that we see here is the original orthotropic linear material, and we see how it's perfectly under tension and compression. The orthotropic bi-modulus linear is similar to the orthotropic linear in tension, but now in compression we have a different modulus. And finally, we have the orthotropic bi-modulus nonlinear. We start to see strain stiffening behavior and under compression strain softening. Now we'll apply this to an actual part and run a multi-scale analysis to show the differences in the results you can get by incorporating the bi-modulus material model. So this is a global part that we're looking at. Very simple. It's a layup that has, I think, 16 plies. And what we're going to do is we're going to apply an RVE that was shown before, and we're going to orient it in the direction, the X direction shown here. So we'll have all the stiffness is going to be really high in the X direction. And we're going to run a 4-point bend test. We're going to fix some node sets on the bottom and the top. So the first set of results I'm going to show are the linear orthotropic material that was used before. So when we're looking at the C111 value, this is the constitutive tensor in the X direction. We can see how the stiffness is universal throughout the part. And even when we run the simulation, we see how it's bending. Nothing changes. It's really constant. That's what the linear orthotropic material model is. And this is translated over to the stresses. When we run the loading in the stress one direction, we can see how we see compression in the top and tension at the bottom. We notice that the maximum of this simulation when we do finally get to the last load step, which is shown here, how we have pretty much an even tension and compression because the modulus is perfectly linear elastic. And in the middle, shown here, we have a value that's very close to 0. So the neutral plane is now directly in the middle, which, as you imagine when you incorporate the bi-modulus, that's not the case. So now, if you incorporate the bi-modulus, we should be getting delamination at other places throughout the component. So now looking at the bi-modulus linear material model. So now this is the same stiffness that I was showing before, but now that we have the bi-modulus, we see how the top is going to be under compression, the bottom is under tension. So we have a greater value in the stiffness on the bottom half as opposed to the top. And you see as we load it, we see a few changes here and there. That's because in the middle, it's a neutral plane. So some elements are going to be under tension, some under compression. And we look at the stresses in one direction, the final load step, when you see now that the tensile stress is much higher than the compressive stress. That's because we have a different modulus in compression now. We now see right in the middle here, we don't have that 0 value of stress. We now have the middle part under tension. So now we can see the neutral plane has shifted as a result of this material model. Finally, we look at the nonlinear bi-modulus. So just like the last simulation, we have a compression on the top and tension under the bottom. But as we run the simulation, we see how the stiffness changes every single load step. You see how progressively we start to lose stiffness in the components under compression. We start to gain stiffness in the elements closest to the bottom. So now you can see a gradient in stiffness going across this component. And the same thing is that we showed before the bi-modulus seen in this in the stresses, and now our neutral plane has shifted once again, which is important because if you have a material that sees nonlinear behavior under tension and compression, it's important to characterize this so you have the correct neutral plane. So that's a demonstration. This can be applied to our standalone system, but we can also apply it to larger components. If you have a plugin and you have a large structure, a lot of times it's represented through shell elements. This works with the plugins now because you have all these different integration points in the top surface and through this section of the shell. So you use one material model, you'll now have the correct bending stiffness as opposed to when you use a material model that has only a constant stiffness and tension compression. Now we will move on to the virtual DMA. So doing a brief background on viscoelastic materials, a linear elastic material as shown here is just constant, there's a constant modulus no matter the strain rate, temperature, loading rate, anything like that. When you have a non-linear elastic material, you can govern the modulus as a function of strain. When we have viscoelastic material, you have a lot of other factors that come into play, two of which are strain rate and now temperature. And you see how energy is dissipated in these materials. A common way to represent these materials is through dynamic mechanical analysis. And what they do is they run at different frequencies and at different temperatures, and they capture a wide range of frequencies at different temperatures. What you can do from this information, you can create a master curve by fitting all these different curves together, and you can have a true representation of a material at any temperature for any loading rate. The issue here is that this test is basically only works for isotropic materials. It's a complex test apparatus. It's really hard to control with a composite material because now you have to load it in the different directions. For example, in the direction of the fiber, we see almost elastic behavior because the fibers are the primary load bearer for this simulation or for this experiment. So the matrix effects are negligible when we run a mechanical analysis in the fiber direction. But when we go to the transverse direction, which is matrix dominated, we start to see the viscoelastic behavior as you can see in this hysteresis curve. So it's really difficult to characterize all these different components, even if you can, you have to run a lot of different tests because these materials are orthotropic. So we're gonna have to get longitudinal, transversal, in-plane shear, out-of-place shear to really characterize this material. What the virtual DMA does, it allows for you to not have to run all these different tests. If you have the isotropic viscoelastic properties of a matrix, that's all you need for a virtual DMA, because we can build a microstructure, put it in a fiber that's linear orthotropic, and we can run a virtual DMA at different temperatures and frequencies at different loadings. So you see here, this is transversely isotropic, so we can run loading the 1-1, 2-2, and 1-2 direction. We can even do in the 2-3 direction if you want. So we'll do a demonstration on the user interface of the virtual DMA. Now, this interface is different from the classic MultiMech GUI, and this is the new MultiMech application user interface. What this is, we have a few different applications, and we build this to streamline some workflows. And we saw the virtual DMA as a pretty unique workflow for including this application. We have a few other different applications like virtual allowables and the tube application. To run analysis, go to DMA, run, insert any name you want for the different material, and we can now locate a RVE that we want to run this simulation. We're not limited to the unidirectional fiber case. In this case, this is the unidirectional fiber case, but you can run this with chopped fiber composites. You run this with a woven structure. Any microstructure they can build through MultiMech, we can run this. So you see in this case, we have some viscoelastic data that's publicly available. So we have this isotropic viscoelastic data with the Prony series and the temperature shift factor. And we have the fiber IM7. So now it's ready to run a virtual DMA analysis. So you input the name, select the path to that file. We can do only a temperature sweep or a frequency sweep or both. Select the minimum and maximum temperatures, the amount of increments in between. Same thing with frequency and the increment, and select the component. When you select run, it'll automatically go through and run the different simulations. Depending on how many you do, you can run hundreds or even thousands of simulations. And these run pretty quick because these are local scale simulations that do one sinusoidal loading. If you look at the results, it will give the option to characterize by temperature or frequency sweep. So we see here we had the different colors, so different temperatures that were done. In this case, it was longitudinal, so we would expect more linear elastic behavior. And you can see this change here, but what you see here, it's very, very small difference from the minimum and maximum modulus. So that's why in the tan delta, we see something that's basically flat. But when we go to the transverse data, we can see how the modulus changes drastically in between the two different temperatures here when we do the frequency sweep. And we can see the loss modulus, tan delta, et cetera. Finally, we have the in-plane shear, which again shows, which is another property that's governed by the matrix, and we can see how this changes as well. The important part here is, okay, we have this data, now what do we do with it? Well, now you can create a MultiMech material model that actually incorporates this data. MultiMech also has a software called Viscolab, so we can export these results to Viscolab. What we can then do is Viscolab will do the temperature shifts and will automatically create the master curve for you. Once you have the master curve, you can extract the Prony series and temperature shift and plug that into MultiMech. And now MultiMech actually has a material model that is anisotropic viscoelastic. So you can control the viscoelastic properties in every single different loading direction. So if you don't want to use the multiscaling approach for running a big layup and running a strain rate dependent simulation, you can now use an anisotropic viscoelastic material using this workflow to run quick simulations and eventually run really large simulations too if you have to look at components that are really large. That concludes the virtual DMA demonstration. So to wrap everything up, we went through MultiMech and the core technology behind MultiMech. We also went through the general new features of the software, and then we took a deep dive in the material database, the Bi-modulus material model, and also the virtual DMA demonstration. So I guess now we can open the floor up, and myself and Flavio can answer any questions you may have. So we have one question so far, and I have a few that were brought in before the webinar too that are in my email. So I'll also ask those as well. So I guess the first question is, you're doing direct homogenization in your software, right? And yes, I think Flavia, you can answer this more completely than I can. So you want to go ahead and answer that?
Sure. Yes. So we do direct homogenization, but it's not the standard approach where one loads the micromodel in all directions. We actually have a unique mathematical formulation that allows us to compute all the homogenizer properties of an RVE in a single shot. Even if the microstructure is evolving, for example, if it has any crack initiation growth, or if it has history-dependent behavior. That's one of the major improvements we made in the software to allow the speed up that Hayden showed before on top of the data compression.
Yeah, thanks, Flavio. Yeah, even before the data compression, we were getting 6x improvements after this methodology, which is pretty cool just from this formulation. All right, another question. Will you update the documentation regarding these new features? Yes, I believe that they're being entered right now. This is kind of the release webinar, so it will be released soon externally to our different customers. So our documentation is still being improved, but it's something that we will contribute to all of our documentation and eventually add new tutorials for going through these new components.
Yeah, we do already have a draft documentation. We just didn't push online, but those will be pushed online very soon. Hayden, I want to add a comment on when you touched on Bi-modulus. I want to mention that we also have, the users now can also combine Bi-modulus with continuous damage models. That's something that we didn't touch.
Yeah, no, that's a good point. These new continued damage models, a lot of times when we want to use continuing damage, like the old software or the old versions, you could only really apply it to isotropic materials. But now you can apply these continuing damage models to any isotropic or orthotropic material, including viscoelastic materials. So you're not limited now to using, a lot of times you have to use failure models to represent the failure or stiffness degradation of these components. And now what we can do is we can incorporate any kind of damage law to a material to expand upon the new continued damage models, one of which is linear exponential decay. You can specify a certain stress in which you expect this to fail. And instead of reducing the stiffness down immediately, you can have more of a gradual failure, which is good for troubleshooting convergence issues, anything like that. Or if you want to characterize the damage a little more as a continued damage basis and show more progressive failure as opposed to sudden failure. A question that we get a lot too is the differences in runtime. So in the example here, we have that 4-point bend. We saw it was like roughly, I'd say 20,000 elements, maybe 30,000 elements there, and we have these microstructures that are linked, so it's fully coupled. And the question is, how long do these take in between all three? And the linear microstructure that we showed is really, really fast. It's homogenized and then you run it. So it's actually pretty close to running with a standard single scale simulation. So that first one we showed was rather quick. The second one now incorporates the Bi-modulus. So we have some slight, we have a difference in the runtime there. But I would say that took about twice as much time as the previous simulation. And then finally, the nonlinear simulation that's going to have a longer runtime, just because we have a lot of different changes across all the different RVEs with the different modulus, and then updating the nonlinear stiffness matrix. So that one took around, I would say, 10 times longer than the linear one, but 10 times faster than a linear model for that regard, which can run pretty quickly. It's still a pretty quick computation time. Okay, we have another question. Can your models predict failure criteria, tension, compression, shear stresses for multiply structure if you know failure criteria for a single ply? Yes. So if we have a multiply structure, we can fail it under tension, compression, or shear stresses. We have a lot of different failure models. We have maximum principal stress and strain. So if you want to just simply fail a ply based on those criteria, that's definitely doable. And we can also fail it according to other composite failure mechanisms that look at combinations of tension, compression, and shear. So like Hessian, Saiwu, etc. A lot of times, though, we don't necessarily need to do that because we already have all our failure criteria and material properties in the RVE. So when it's failing, the RVE will fail and lose all its stiffness, similar to a failure model, but it's actually being represented by an RVE. You want to expand upon that at all, Flavio, regarding the methodologies we take for modeling failure in the ply versus in the microstructure?
I think you covered that well. I might just add that, of course, the quality of the prediction will depend on the quality of the models, like how well are you modeling the resin and fiber, for example. If you only have single ply data, you can fit multiple models to the same experimental data of a single ply, especially for the resin. So what we try to do when we partner with clients is to really capture the physics and understand what happened in the experiments, what are the specificities of the resin and fiber, and choose the right model for those.
Mm-hmm. Yeah, and when we're looking at just single plies, that was kind of like the first step for let's just represent the ply accurately through microstructure, but we can keep going deeper and deeper, and we have done this before where we look at more complex things like the interlaminar region. You have a resin-rich region in between these plies, that might be maybe 100th or 1,000th of the thickness than the ply. But this is where a lot of failure happens. You have the interlaminar failure, and a lot of times you represent it through a cohesive zone, but we try to get away from that. We're now representing it through these things called multi-scale cohesive zones. So that's something that we can also do and represent the physics. And the whole point of MultiMech is to try to represent every single aspect of physics, whether that's representing generalized failure of a microstructure, representing crack propagation, which is a big component of our software as well. Okay, and I had another question before this that was asked beforehand. I was generally inquiring about these new capabilities. Will they be reflected in all the new plugins? Like a lot of our customers are concerned about is that a lot of them use the plugins, whether that's ANSYS, Abacus, or MultiMech or MultiMech standalone. Sorry, or NX Nastran. And will these all be reflected? And the answer is yes. In the 19.0 release, all the different changes you see within MultiMech standalone are available within the plugins. So, like I had mentioned earlier, with if you have a large Abacus model, you can now run these material models that were just talked about today. You can start building a material database. So a question that was asked is, do you have hyperelastic damage models also? So I'll give a very brief explanation on that, but I think Flavia, that's best for you. But basically, we have not got to hyperelastic material models yet. And Flavio, do you want to explain why?
Yeah, so if hyperelastic, if you mean by large deformation, we do not have large deformation at this point. That's something we are working on. But you can account for the strain stiffness with the Bi-modulus nonlinear model that Hayden touched before. So the question is not clear to me. If you want to more detail or rephrase the questions or touch base afterwards, we'll be happy to do so.
Yeah,
and one of the reasons why we don't have finite deformation yet is because, for example, for composite materials, fiber reinforced composite materials, they don't really undergo very large strains. They typically fail before that. But we do add a lot of nonlinear models, even though it's not large deformation.
Yeah, and yeah, I think that's something that's also, we're constantly working on and trying to add these different things, because hyperelastic models, are starting to be, elastomers are starting to be applied to composites as well. So that's something that is, being, worked on the R&D side. It's not ever clear exactly how soon they'll be here, but there has been some interest in using, representing elastomers. But we want to first represent, these more, widely used materials first before jumping into something that uses these large deformation, more advanced finite element models.
Yep, I think you brought a very important point, Hayden, which is our technology is very generic and can be applied to multiple materials. Right now, we have a lot of use cases for fiber reinforced composites, but we have also done work with metals, iceberg ice, asphalt materials. And we are starting to see more interest from elastomers, as you mentioned. And as we find more application, that's when we expand the capabilities of the software in terms of physics and numerics.
All right, thanks for expanding upon that. So we don't have any more questions. Within the next few seconds, please ask your question. We can talk about it, but I think we can conclude this webinar, conclude it a little bit early. That's okay. The recording of this webinar will be sent to you automatically, as well as anyone that has signed or registered for the webinar. I'd like to thank everyone for attending today. And if you have any more questions, feel free to go to our website, www.multimechanics.com. You will have there's a lot of technical resources there where you can go through and see, papers we published or different, webinars in the past that we've put out. You can download the recording there as well. And you can also get in contact with us. And like Fabio said, we can set up a meeting if you have more questions and you want to talk about your own engineering projects and problems that you may have. Yep. Thank you very much, everyone, and have a good day.
Thanks, Hayden. Thanks, everyone, for attending the webinar.